All right, question 3. Now we're talking about mechanism for a radical addition. Many of you ignored the peroxide part entirely, which would also mean that you have no way of explaining that product, because without the peroxides, the bromine ends up on the upper of the two alkene carbons, not the lower one that you're seeing here. So that's important. Now, it works by a radical mechanism. Peroxide's a big giveaway that you're looking at a radical rather than a polar mechanism. We went through this in the videos for this chapter. It's important because it's the only way, in the case of halogenation like this, that we can get around the cation stability preference. So let's look at it. So first, we have the initiation steps. In this case, that's peroxide of some form. Just drawing hydrogen peroxide here, undergoing probably a thermal cleavage. If we heat it up, it will break down and give me two radicals. That's the important initiation step. Propagation, there will be multiple ones because we have a lot of different steps where we begin with a radical and end with a different one, rather than the initiation where we start with no radicals and end up with two, and eventually termination where we start with two radicals and end with none. But propagation is one used, one formed. So, first propagation step will be getting the HBr involved. The peroxide is just there in a very small amount to allow us to actually get this started. So it's like a match in terms of lighting a fire. It's not there, not necessary to be there in large amounts. You just need something to kick things off. So basically, it's the way that we get to this. We've got water, and we've got our first useful radical, the bromine one. Now, at that point, we have propagation step number 2. I'm going to use Roman numerals here just so we can keep track of them. We have our alkene. In this case, I use a cyclohexene. And we have our bromine radical. The alkene is going to give up an electron to form a bond with the bromine. The bromine had a radical there. So now I have the attachment that I needed. Now, why does it end up forming a radical there instead of giving me the same regiochemistry that the ionic addition does? And it's because this is a radical behaves more like a cation. So the same reasons why a cation would be more stable than a tertiary carbon, meaning more hyperconjugation, exactly the same thing here. The radical is still behaving like it's half empty in terms of electron density. It is stabilized by more alkyl groups around it. Therefore, that is the better radical. That controls our regiochemistry. Very much like it did with the cation case, only we're getting an opposite answer here because of the reagents involved. Now, we have that radical on our cyclohexane, and we have more HBr. So this now takes hydrogen, and the bromine is left as a radical. So we get this. We now have a hydrogen here. There's no implied stereochemistry. And our leftover is the bromine radical. So that goes back into the job here and becomes a cycle, which is common to all radical reactions. Now, you didn't have to draw terminations here because that's not about getting to the actual product, but for completeness, you really should. Any two radicals you see here can combine in a termination step to form a bond. Any two radicals, doesn't matter which ones. So I could have this one and the bromine radical. I could have two bromine radicals get together. I could have a hydroxide, technically, and a bromine radical get together. I could have two carbon radicals get together. So in terms of getting a radical process like this to work properly, we can't have a lot of radicals around at any given moment because we're going to have too many termination steps. So what we want is a very small amount of initiation, which then keeps the amount of this very small, and then that in turn keeps this concentration very small, and we never get much of them, so the chances of two radicals running into each other is minimized. That's the real trick to a radical process, is keeping the actual amount of radicals around in solution to a minimum without stopping the reaction.